This is the last lesson in the unit and the last word problem lesson for a while. Again, hopefully you're seeing I can rewrite a variable in terms of another variable. That's the common theme the last three lessons. These are probably the hardest of the three, though. The distance, rate, time problem. I call them dirt problems, and you'll see why in a second. To find an object's distance traveled, you can multiply its rate and time. Okay, so the distance is d equals rate times time. And this is where dirt comes from. D, another word for equals is, so D-I-R-T, dirt problems. That's what you'll hear me say. Okay, a simple example of this. If you travel 40 miles per hour, which miles per hour is a rate, for 3 hours, that is the time, how far would you have traveled? 40 miles per hour times 3 hours, it'd be 120 miles, which is the distance. So in this lesson, we're going to look at two types of travel. Same direction travel, where the distances are equal, okay, and opposite direction travel, where the distances are added together. And we're going to do same direction first, okay? A train leaves a station at 1 p.m., traveling at an average speed of 60 miles per hour. A high-speed train leaves the same station 2 hours later, traveling 20 miles per hour faster than the first train. The second train follows the same route as the first train on a parallel track. In how many hours will the second train catch up to the first train? Okay, so let's draw a picture to see what's happening. So we've got train 1 and train 2. Train 1 leaves first, right? And it leaves the station. Let's say this is the station. This line is the station. And it leaves and it travels to a certain spot. This one leaves 2 hours later, right? So it says it leaves 2 hours later. But it goes along the same route. So it's going parallel to the first train. And I'm asking when and how many hours will the second train catch up to the first train? So we're going to stop, basically, think of it as a stopwatch. We're going to stop it when they become equal. So that represents the distance traveled. Well, they both travel the same distance from the station to when they meet. The difference is how long it took to get there and how fast they went. But we're getting ahead of ourselves. Let's first define our variable. That is key number one. It helps a ton if you can do this correctly. Does it matter? Technically, it does not matter. But we can be smart about it. If I'm looking at this, it says, in how many hours will the second train? I care about the time for the second train. So in how many hours will the second train catch the first train? I can define my variable that way. So I'm going to say, and how many hours, I'll say h is number of hours for train 2, specifically train 2. Now, once you define the variable, you can fill in a table. Now this table, what it means is, let me just have train 1, train 2, the rate of one of them, the time of one of them, and the rate of the other one, and the time of the other one. We may know some of those and we may not. Okay, so right now, I'm going to put my variable in the box. That's what I'm going to do first. So where does h go? So it's the number of hours. So it's going to be a time, but for which one? Train 2. So I'm going to put my h in train 2's time. Now I'm going to look back at the problem. The first train is going at an average speed of 60 miles per hour. Okay. So the first train rate is 60 miles per hour. The high-speed train leaves the same station 2 hours later, traveling 20 miles per hour. Wait a second, that's not faster. But it says 20 miles per hour faster than the first train. So what's 20 miles per hour faster? 60 plus 20. It's going 80. Now the one box we have remaining is the time spent for the first train. Now, this is the confusing part. Okay? Time is figured by looking at how much time is spent traveling for each train. Okay? So, if this train took, I don't know, let's just make up a number. 4 hours. Let's say it takes 4 hours. How long has train 1 been moving on the track? Well, it says train 2 left 2 hours later. which means it's been traveling for less time than train 1. Another way of saying that exact same thing is train 1 has been traveling for a longer amount of time. How much longer? 2 hours longer. So train 1 has been traveling for the same number of hours as train 2 plus 2 more hours because he left earlier. So that's the time for train 1. That's the relationship between the time for train 2 and the time for train 1. That could be 2 different variables, but I don't want to have 2 different variables. I want to have a variable in terms of another variable. Okay? Now, I get people that get confused on this part too. I want to write an expression representing distance. A lot of people look for a number. How far do they travel? Well, we don't know that. It doesn't say anything about how far they traveled. We just know they traveled the same amount of distance. But if you keep in mind that rate times time gives me distance, you can write an expression that represents the distance. So for train 2, it traveled 80 miles an hour for h hours. So it traveled 80 miles. So that's a distance right there. For train 1, it was 60 times h plus 2. Also a distance. So we're going to come back to that in a second. Since we know that these trains covered equal distances, we can set up an equation using the expressions representing each train's distance. So I can say 60 times h plus 2, which is how far train 1 went, equals 80h, which is how far train 2 went. And now we just solve. So 60h plus 120, I distributed, equals 80h. I'm going to get my h's together, subtract 60h. I get 20h. Divide by 20, I get h equals 6. So how long did it take the second train to catch up? Well, if we define our variable that way, it took the second train 6 hours. What time of day was that? So you have to think about time. If the first train left at 1, it traveled for 6 plus 2. It had been traveling for 8 hours. What's 8 hours later than 1 p.m.? It would be 9 p.m. If you look at it as far as train 2, if the slow one left at 1, the fast one left at 3, 2 hours later, and traveled for 6 hours. 3 plus 6, 9 p.m. Okay? Now we're going to do opposite direction travel. Okay, I know this is probably confusing, blowing some people's minds, but stay with me if you can. 2 jets leave Dallas at the same time and fly in opposite directions. One is flying west, so let's call this Dallas here. One is flying west, 50 miles per hour, faster than the other. Okay, so it's flying west. The other, and it's going faster, so it's going to go further. This one's traveling east, so it's going slower. Okay? After 2 hours, the jets are that far apart. Find the speed of each jet. So I need to find each one. So you get to pick which variable you want to use. So I'm going to go with W is the speed of the west flying jet. Okay? I'm going to jump ahead real quick. I'm going to do alternate table. You don't have to do both of these. I want to make sure you understand that. I'm just showing you what it would look like if you had defined your variable a different way. That's why I'm jumping over here. So let's say I would have done the other one. Let's go with E for speed of east jet. And now we'll fill in both tables kind of at the same time. So the speed of the west jet, I'm going to put that in for W. I'm going to put W in right there. Down here, the speed of the east jet, I'm going to put that here. Well, if I look at it, the one flying west is going faster than the east. Okay? So west is going faster than east. Or another way of saying that is east is traveling slower than west. And how do I show slower? I would do the speed of the west jet, and I would subtract 50. Over here, the west jet is going faster, so it's going the east jet speed plus 50. Do you see the difference in the two? and that is only depending on how you define your variable. The time that they've been flying, well, it says after 2 hours. So both of them were traveling for 2 hours. So that's the same number on both of them. Okay? Now, a lot of people look at that and say, oh, they're 2,500 miles apart, so the distance is 2,500. No, the 2,500 is how far apart they are. It's not how far each of them went. So they could have gone, I don't know, 2,000, and they could have gone 500. These could have gone 1,500. These could have gone 1,000. We don't know. So we still have to write an expression for their distance. So for the west jet, it would be 2w. For the east jet, it would be 2w minus 50. Down here, it would be 2e plus 50, and then 2e. Now, I've already explained this, but since we know the jets covered unequal distances, we can set up an equation to solve the problem. Let's go from table 1 first. So 2w is how far the west jet went. So that's this. This one would be 2w minus 50. If I add those two up, 2w plus 2w minus 50, that's going to give me 2,500. Here, I would do 2e plus 50 plus 2e equals 2,500. And you're going to see, if I solve both of those, you should get one of the right answers. So I'm going to solve the first one here. So 2w plus 2w minus 100, I distributed the 2, by the way, equals 2,500. So that's 4w minus 100 equals 2,500. Add 100, I get 4w equals 2,600. Divide by 4, I get 650. So that's the west flying jet, 650 miles per hour. How would I get the east flying jet? I take 650 minus 50, and I would get 600 miles per hour. But let's say I would have solved the second equation. So that's 2e plus 100 plus 2e equals 2,500. So that's 4e plus 100 equals 2,500. I'd subtract 100, I get 4e equals 2,400. Divide by 4, I would get e equals 600. And you're like, those aren't the same. You'd be right. But remember, that's the east jet, which is 600, and then you would take e and you'd add 50 to get the west jet. So just, if you did this table, you would be finding the west jet first, the speed of the west jet. If you did this table, you'd be finding the speed of the east jet, and you just have to plug it in and figure out the other one. Okay? I know I went through that quickly. I know it's probably confusing. We're going to spend time on this, but yeah, hopefully you got everything down.